Okay, in this video I'm going to begin section 14.3. So a Hamilton path in a graph is a path that uses every vertex of the graph exactly once. A Hamilton circuit in a graph is a circuit that uses every vertex of the graph exactly once. Remember, a circuit is one whose start and end point is the same. Okay. Problem 25. Consider the graph shown below. Okay, find a Hamilton path for the graph. Okay, so if I go A to B to C to D to E to F to G to H. Okay, I've used every vertex of the graph exactly once. Okay, find a Hamilton circuit for the graph. So I've got to use every vertex once, and the start and end points have to be the same. Okay, so if I go B to A to D to C to H to E to F to G and then back to B. Okay, I would have found a circuit since the beginning, since the first and last vertices were the same. Problem 26. Determine whether each sequence of vertices is a circuit, whether it is an Euler circuit, and whether it is a Hamilton circuit. Okay, so part A, if I go A to B to C to D to E to F to G to A. Okay, so yes, that would be a circuit. Now, is it an Euler circuit? Well, no, an Euler circuit is a circuit where you got to touch it at least, or you've got to hit every edge exactly one time. And so, no, we didn't do that. Is it a Hamilton circuit? No, because I didn't hit vertices I and H. Okay, so part B. Okay, is this a circuit? Well, the first and last vertices are the same. Okay, B to I to G to F to E to D to H to F to I to D to C to B to G to A to B. Okay, so yeah, that would be a circuit. I didn't touch any edge more than one time. It is an Euler circuit since the first and last vertices are the same, and I touched every single edge exactly one time. It's not a Hamilton circuit though, because, for example, B is used more than one time, and there's some other vertices there. D is used more than one time. So with a Hamilton circuit, you can only touch each vertex exactly one time. Okay, and the first and last vertices have to be the same. How about part C? A to B to C to D to E to F to G to H. Well, G and H don't join, right? So no, there would be no circuit at all since G and H don't join. Okay. Problem 27. Determine whether an Euler circuit, a Hamilton circuit, or neither would solve the problem. Part A. The vertices of a graph represent the bandstands at a festival, and the edges represent paths between the bandstand. A visitor wants to visit each bandstand exactly one time, returning to her start point when she is finished. So that would be an example of a Hamilton circuit. She's going to visit each bandstand exactly one time, and we don't care about all the edges that would go from one bandstand to the other bandstand. Part B. The vertices of a graph represent places which where paths in a botanical garden cross, and the edges represent the paths. Okay, a visitor wants to walk along each path in the garden exactly one time, returning to his start point when finished. So that would be an example of an Euler circuit because the visitor is going to walk along each path exactly one time. Okay, and each path would be represented by an edge. Also, it's going to be a circuit since he's going to return to his start point when he's finished. Okay. Problem 28. A complete graph with n vertices will have n minus 1 factorial Hamilton circuits. How many Hamilton circuits are in the complete graph shown below? Okay, so I got a graph with 6 vertices. 6 minus 1 is 5. 5 factorial, 5 times 4 times 3 times 2 times 1 is 120 Hamilton circuits. Okay, so there'd be 120 Hamilton circuits total in this picture if I were to check all those. Okay. Definition: a weighted graph is a graph with the edges labeled with some quantity of interest. These labeled quantities are the weights of the graph. Okay. In a weighted graph, a minimum Hamilton circuit is a Hamilton circuit with the least possible total weight. Okay. Definition: one approximation algorithm for finding a minimum Hamilton circuit in a weighted graph is the nearest neighbor algorithm. The steps for using this algorithm are below. Okay, so step 1, I'm going to choose a starting point for the circuit, call this vertex A. Step 2, I'm going to check all the edges joined to A and pick the edge with the smallest weight. Proceed along this edge to the next vertex. Step 3, at the next vertex, pick the edge with the smallest weight that does not go to a vertex already used. Step 4, I'm going to repeat step 3 until I've visited all the vertices. Step 5, I'm going to return to the vertex A to complete the circuit. Okay, so as an example, problem 29, a regional manager decides that she needs to visit all of the company locations in her region during the last few weeks in August. She lives in city A and she needs to visit cities B, C, D, and E, and then return home. The driving time, which is in minutes, between the cities is shown below. Use the nearest neighbor algorithm to find a route that will give her the least amount of driving time. Okay, so she lives in city A, so she's going to start in city A. So I need to check all the edges that join into A, and I just simply pick the one with the least weight. Okay, so 200, 415, 390, and 240, 200 would be the one that has the least weight. Okay, so now I'm at vertex B, and I do the same thing. I pick the edge that has the least amount of weight. 350, 510, 310. Okay, it'd be 310. Okay, so then I'm at vertex C. Now again, I don't want to form a circuit unless I visit all the vertices. Let's see, at 415, at 410, 425, so 410, I take down to E, and so from E I have to go to D, right? Because D is the only place that I haven't been to. So I'm going to have to go to D and then back to A. So let's see, I've got the weights of all that written down there. So the driving time that she would have taken if she would have taken this particular path would be 1,685 minutes total. Okay. As a note, the nearest neighbor algorithm isn't guaranteed to find the actual optimal solution, or the one that has the least amount of weight. In the previous problem, there are 2 paths that have a driving time of 1,550 minutes. Okay. This algorithm is just simply one that finds an approximate optimal solution. There are other algorithms that can be used to find the approximate solutions as well. Okay, so problem 30, consider the graph that's shown below there. We've got a weighted graph, and part A, we're going to use the nearest neighbor algorithm, starting at each of the vertices, in turn to determine an approximate solution to the path or to the problem of finding a minimum Hamilton circuit for the graph. In each case, find the total weight of the circuit. Okay, so if I start at A, then let's see, 13, 60, 58, and 16. I'm going to go A to E. And then from E, if I take, let's see, 2, 8, and 6, so it'd be to B, A to E to B. And then from B, I have to go to either to C or to D. So let's see, at a 9 and 14, so from B I go over to C, and then I got to go down to D, right? So that'd be 11, and then from D back to A. And so if I take that particular path, I would have taken, 95, whatever the units are, minutes or whatever. Okay. So what if I'm starting here at B? Well, from B, okay, so there's 16, 2, 14, and 9, so I go B to E, and then from E, let's see, out of 13, 8, and 6, I go E to D. To D, I only have to go to C or to A, so so 60 or 11. Okay, I need to go to C, and from C I have to go to A, and then back to B where I started from. Okay, and if I take that particular circuit, it would have taken 95 minutes, I guess. Okay, and so starting at C, if I go C to, let's see here, 9, 58, 8, and 11, so if I go C to E, and then from E, I go 13, here's 2, and then 6, so E to B. Okay, so C to E to B. From B, I either got to go to A or to D. So 16 versus 14, so B to D. D over to A, and then over to C. Okay, and if I take that, it's going to take 142 as the optimal time. Okay, what if I start at D? Okay, from D, let's see, 6, 60, 14, and 11. So from D, I got to go to E. From E, looking at 13, 2, or 8. Okay, so 2. So it's D to E to B. And then from B, either go to A or C. So 16 versus 9. Okay, so go to C. C to A, and then back to D. Okay, so that would be 135 is the total there. Okay, what if I start at E? Okay, well, if I start at E, let's see, from E, I'm looking at 16, 2, 8, and 6. Okay, so go E to B. From B, let's see, it goes 16, 14, and 9, so B to C. From C, and let's see, I can either go to A or to D, so I'm looking at 58 or 11. Okay, take 11, so that's E to B to C to D. And then from D, I have to go to A and then back to E. Okay, and if I take that route, then 95 is the total weight for the circuit. Okay, so you can see that how the weights are going to differ depending on which, what your start point is. Part B of this, which of the circuits found in Part A give the best solution to finding to the problem of finding a minimum Hamilton circuit for the graph of for this graph? Well, so I just simply look at the one that produced the smallest weight, which would be the second one here. And that'd be the circuit that started at B, it looks like, produced the least amount of weight. Now just by looking carefully at the graph, find a Hamilton circuit in the graph that has a lower total weight than any of the circuits found in part A. Okay, so if I take a look at, if I start at, I like the 2 there, so if I start at B and then go to, let's see, B to A, and then A to E, and well, yeah, so if I go to avoid these like higher markers, so B to A to E to D to C to B. Well, if I take this pentagon around, I would go, let's see, that's going to give me 55, okay, which is smaller than all these other ones that I'm getting there. Yeah, that's it for section 14.3 there. The homework in this section is on page 841. So we've got one more section left to cover, which is section 14.4. We'll hit that one next.